Okay, so this video is meant to illustrate a couple of different things. It's to serve as a practice problem. It's to show you one way of representing molecules. That's a very old-timey way of doing it. It is to give you practice in working with actual models, all sorts of things I'm trying to do here. So what I've done for you is draw two molecules next to each other on the board, and they are in a Fischer projection, which is a very old-school way of representing things, but it's a way that biochemists often use to represent sugars and things like that. So anyway, this is a very old way of representing molecules, but it's also one that you will encounter in the future, and so it's worth wrapping your head around it, but it also serves as an opportunity to sort of illustrate other principles, so that's the main reason why I'm doing it. So it's an old-time way of doing it that basically looks like this. Any single vertex is, of course, a carbon atom, as always, but things coming horizontally off are toward the camera, and things going vertically are back into the board. And so in other words, R1 and R2 are both back behind this point, but R3 and R4 are both coming out toward the camera. If I'm trying to represent one of the molecules in question, it might be like this, where what I have are the two red OHs. This is an OH right here, and this is an OH. They're coming toward the camera, as are these two hydrogens, not labeled. Going back away from the camera are the methyl, and then, of course, the carbon-carbon double bond. Now, my recommendation, if you want to follow along, would be to stop and go ahead and build this model kit, and then you will find it easier to do the various transformations. But one of the reasons why I like Fischer projections is because it allows you to see at a glance how the molecule you have built relates to the one next to it. So what is the relationship between these two molecules? What is that blue thing? That is, of course, a mirror plane. Therefore, the relationship between these two is enantiomers. And so, of course, if you've got both model kits built, then you can start playing with them, trying to superimpose them, and so on and so forth. But as you can tell, they are reflected in the mirror, so they are clearly they are clear mirror images. And then once you try superimposing these on top of each other, what you'll quickly realize is that if you have the double bonds aligned with each other and the methyls aligned with each other, then the OHs end up on opposite sides. So this is clearly non-superimposable mirror images. Two other points I want to make here. One is, this is not ordinarily the way we'd represent these molecules, so it's useful to work on sort of unfolding this into the more normal staggered conformation. So we'll work on that problem. But then the other is, if I were to flip one of these stereogenic centers, but not both, then I would create a new molecule. And so let's just go ahead and do that. What is the relationship between these two molecules? Well, I have flipped one stereogenic center, but not both. Therefore, they are diastereomers of each other. And that's obviously true for these two, which is how I generated it. I'm keeping this OH the same side, but flipping this stereogenic center. On the other hand, these two molecules are also going to be diastereomers of each other, because of course this OH on top is the same, but the other one is flipped. The relationship between these two molecules is diastereomers, as is the relationship between these two. The relationship between these two, they are enantiomers. But if I wanted to generate the enantiomer of this, what would I do? Well, I'd start by drawing a mirror plane somewhere and then reflecting the molecule. So now, of course, the relationship between these two molecules here that I drew at the outset is that they are enantiomers of each other, and the relationship between these two molecules, again reflected across the mirror plane, is that they are enantiomers of each other. Okay, and the last thing I wanted to do here is to show you how I do the unfolding process, and to tell you that this is a skill that you need to work on, so you might as well practice it. So first I would grab the model that actually matches what I have drawn, which is to say this is the model that relates to that particular structure. And then the way I do this, if I had the model kit, is I would just simply take this model like that and then rotate it in such a way that the carbons end up staggered, and then read off what the values are, and that would be how I would do it. But the main reason to show you this is to show you that this can be done by drawing it out on paper and not using the model kit at all. And so what I would do first is to say, okay, this double bond is going to be going back relative to the carbon that's right here, which then itself goes down to the carbon that's down here, which then itself goes down to the carbon that's the bottom methyl, as follows. And then what we have is the OH coming, both of those would be coming up toward us, and then the H on the right in both cases would be coming up toward us. And then, to make my life easier to follow, what I would then do is take this molecule and rotate it 90 degrees around the vertical axis so I can kind of see what I'm looking at a little bit better. So in other words, I would have the double bond kind of over here, and then that goes to that particular carbon right there, and then I go straight down to the next particular carbon, and then I come back down to the methyl. So all I've done is basically rotate it so that the OHs, which were up and toward me when I rotate this way, now they're going to be up and out. Meanwhile, the H's should be back into the board. And now what I'm going to do is I'm going to rotate around this single bond. So I'm not going to rotate the molecule anymore, but I'm going to rotate around this single bond. So that's what I want for the staggered final carbon chain. And now I need to figure out where everything is going to be. So the OH was up and toward, and as I rotate it, it's going to end up down and back. And the H is going to end up and toward me. And if you can't see why that's the case, that's the value of working with the models. So I've rotated that so that's down and back, and then I'm going to go ahead and try to figure out where this H is, and I'm also going to rotate around this bond as well, as the case may be. So I need to rotate around both of those. Eventually, this OH ends up and toward us, and the other H ends up back. So again, the process is basically as follows. You first draw the molecule the way it actually looks. So first build it, actually. So you build the molecule, make sure that it matches up like that. But then you draw the molecule. So this double bond is behind this carbon. This carbon then ends up vertical, and then the methyl ends up behind this carbon. So that's what I have. And then I rotate it sideways 90 degrees. So now the OHs are pointing toward you, and that's like that. And now I basically rotate everything until I end up with the staggered conformation. And now this OH is behind this carbon, this OH is in front of this carbon, and that's the molecule right. This is, of course, an exercise that forces you to think in 3 dimensions in a useful way, which is why it's valuable. And it also forces you to work with the model kit. So my recommendation would be to draw a couple of these and then play with the models until you can do the manipulations in your head. It's really a question of getting better at seeing the 3-dimensional rotations without needing to use the model, but also being able to use the model to check yourself. And so this is a valuable exercise no matter what. So practice this kind of manipulation. You will find it a useful exercise in the long run.